In mathematics and computer algebra, factorization of polynomials or polynomial factorization is the process of expressing a polynomial with coefficients in a given field or in the integers as the product of irreducible factors with coefficients in same domain. Polynomial factorization is one of the fundamental tools of the computer algebra systems. The history of polynomial factorization starts with Hermann Schubert, who in 1793 described the first polynomial factorization algorithm, and Leopold Kronecker, who rediscovered Schubert's algorithm in 1882 and extended it to multivariate polynomials and coefficients in an algebraic extension. But most of the knowledge on this topic is not older than circa 1965 and the first computer algebra systems. In a survey of the subject, Eric Kaltofen wrote in 1982, "When the long-known finite-step algorithms were first put on computers, they turned out to be highly inefficient. The fact that almost any uni or multivariate polynomial of degree up to 100 and with coefficients of a moderate size can be factored by modern algorithms in a few minutes of computer time indicates how successfully this problem has been attacked during the past 15 years. Nowadays one can quickly factor any univariate polynomial of degree 1000, and coefficients with thousands of digits." Formulation of the question. Polynomial rings over the integers or over a field are unique factorization domains. This means that every element of these rings is a product of a constant and a product of irreducible polynomials. Moreover, this decomposition is unique up to multiplication of the factors by invertible constants. Factorization depends on the base field. For example, the fundamental theorem of algebra, which states that every polynomial with complex coefficients has complex roots, implies that a polynomial with integer coefficients can be factored into linear factors over the complex field C. Similarly, over the field of rails, the irreducible factors have degree at most 2, while there are polynomials of any degree that are irreducible over the field of rationals Q. The question of polynomial factorization makes sense only for coefficients in a computable field whose every element may be represented in a computer, and for which there are algorithms for the arithmetic operations. Froelich and Shepperson have provided examples of such fields for which no factorization algorithm can exist. The fields of coefficients for which factorization algorithms are known include prime fields and their finitely generated field extensions. Integer coefficients are also tractable. Kronecker's classical method is interesting only from a historical point of view. Modern algorithms proceed by a succession of square-free factorization, factorization over finite fields, and reductions. From the multivariate case to the univariate case, from coefficients in a purely transcendental extension to the multivariate case over the ground field, from coefficients in an algebraic extension to coefficients in the ground field, from rational coefficients to integer coefficients, from integer coefficients to coefficients in a prime field with p elements, for a well-chosen p. Primitive part content factorization. In this section, we show that factoring over Q and over Z is essentially the same problem. The content of a polynomial pz(x), denoted cont, is, up to its sign, the greatest common divisor of its coefficients. The primitive part of p is primpart equals p cont, which is a primitive polynomial with integer coefficients. This defines a factorization of p into the product of an integer and a primitive polynomial. This factorization is unique up to the sign of the content. It is a usual convention to choose the sign of the content such that the leading coefficient of the primitive part is positive. For example, is a factorization into content and primitive part. Every polynomial Q with rational coefficients may be written where pz(x) and cz. It suffices to take for C a multiple of all denominators of the coefficients of Q and P equals CQ. The content of Q is defined as and the primitive part of Q is that of P. As for the polynomials with integer coefficients, this defines a factorization into a rational number and a primitive polynomial with integer coefficients. This factorization is also unique up to the choice of a sign. For example, is a factorization into content and primitive part. Gauss proved that the product of two primitive polynomials is also primitive. This implies that a primitive polynomial is irreducible over the rationals if and only if it is irreducible over the integers. This implies also that the factorization over the rationals of a polynomial with rational coefficients is the same as the factorization over the integers of its primitive part. On the other hand, the factorization over the integers of a polynomial with integer coefficients is the product of the factorization of its primitive part by the factorization of its content. In other words, integer GCD computation allows to reduce the factorization of a polynomial over the rationals to the factorization of a primitive polynomial with integer coefficients, and to reduce the factorization over the integers to the factorization of an integer and a primitive polynomial. Everything that precedes remains true if Z is replaced by a polynomial ring over a field F and Q is replaced by a field of rational functions over F, in the same variables, with the only difference that up to a sign must be replaced by up to the multiplication by an invertible constant in F. This allows to reduce the factorization over a purely transcendental field extension of F to the factorization of multivariate polynomials over F, square-free factorization. If two or more factors of a polynomial are identical to each other, then the polynomial is a multiple of the square of this factor. In the case of univariate polynomials, this results in multiple roots. In this case, then the multiple factor is also a factor of the polynomial's derivative. In the case of univariate polynomials over the rationals, Lll algorithm exploits this to factorize efficiently the polynomial into factors that are not multiple of a square and are therefore called square-free. To factorize the initial polynomial, it suffices to factorize each square-free factor. Square-free factorization is therefore the first step in most polynomial factorization algorithms. Lll algorithm extends to the multivariate case by considering a multivariate polynomial as a univariate polynomial over a polynomial ring. In the case of a polynomial over a finite field, Lll algorithm applies only if the degree is smaller than the characteristic, because, otherwise, the derivative of a non-zero polynomial may be zero. Nevertheless, a succession of GCD computations, starting from the polynomial and its derivative, allows to compute the square-free decomposition. See Polynomial Factorization over finite fields #square-free factorization. Classical methods. This section describes textbook methods that can be convenient when computing by hand. These methods are not used for computer computations because they use integer factorization, which at the moment has a much higher complexity than polynomial factorization. Obtaining linear factors or linear factors with rational coefficients can be found using the rational root test. If the polynomial to be factored is, then all possible linear factors are of the form, whereas an integer factor of n is an integer factor of. All possible combinations of integer factors can be tested for validity, and each valid one can be factored out using polynomial long division. If the original polynomial is the product of factors, at least two of which are of degree 2 or higher, this technique only provides a partial factorization, otherwise the factorization is complete. In particular, if there is exactly one nonlinear factor, it will be the polynomial left after all linear factors have been factorized out. Note that in the case of a cubic polynomial, if the cubic is factorizable at all, the rational root test gives a complete factorization, either into a linear factor and an irreducible quadratic factor, or into three linear factors, Kronecker's method, since integer polynomials must factor into integer polynomial factors, and evaluating integer polynomials at integer values must produce integers. The integer values of a polynomial can be factored in only a finite number of ways, and produce only a finite number of possible polynomial factors. For example, consider, if this polynomial factors over z, then at least one of its factors must be of degree 2 or less. We need 3 values to uniquely fit a second-degree polynomial. We'll use, and note that if one of those values were 0, then you already found a root. If none is 0, then each one has a finite amount of divisors. Now, 2 can only factor as 1 times 2, 2 times 1, times, or times. Therefore, if a second-degree integer polynomial factor exists, it must take one of the values 1, 2, minus 1, or minus 2, and likewise it. There are 8 different ways to factor 6, so there are 4 times 4 times 8 equals 128 possible combinations, of which half can be discarded as the negatives of the other half, corresponding to 64 possible second-degree integer polynomials that must be checked. These are the only possible integer polynomial factors if testing them exhaustively reveals that constructed from and factors dividing by gives the other factor, so that now one can test recursively to find factors of n. It turns out they both are irreducible over the integers, so that the irreducible factorization of is modern methods. Factoring over finite fields, factoring univariate polynomials over the integers if is a univariate polynomial over the integers. This way, if is an integer larger than, and if is known modulo, then can be reconstructed from its image mod. The Zassenhaus algorithm proceeds as follows. First, choose a prime number such that the image of mod remains square-free, and of the same degree as. Then factor mod. This produces integer polynomials whose product matches mod. Next, apply Hensel lifting. This updates the in such a way that now their product matches mod, where is chosen in such a way that is larger than. Modulo. The polynomial has factors. For each subset of the product is a factor of mod. However, a factor modulo need not correspond to a so-called true factor, a factor of in. For each factor mod, we can test if it corresponds to a true factor, and if so, find that true factor, provided that exceeds. This way, all irreducible true factors can be found by checking at most cases. This is reduced to cases by skipping complements. If is reducible, the number of cases is reduced further by removing those that appear in an already found true factor. Zassenhaus algorithm processes each case quickly. However, in the worst case, it considers an exponential number of cases. The first polynomial time algorithm for factoring rational polynomials has been discovered by Lenstra and Lovers and is an application of Lenstra-Lovers lattice basis reduction algorithm, usually called Lll algorithm. A simplified version of the Lll Factorization algorithm is as follows. Calculate a complex root alpha of the polynomial to high precision. Then use the Lenstra-Lovers lattice basis reduction algorithm to find an approximate linear relation between 1, alpha, alpha 2, alpha 3, with integer coefficients, which might be an exact linear relation, and a polynomial factor of. One can determine a bound for the precision that guarantees that this method produces either a factor, or an irreducibility proof. Although this method is polynomial time, it was not used in practice because the lattice has high dimension and huge entries, which makes the computation slow. The exponential complexity in the algorithm of Zassenhaus comes from a combinatorial problem. How to select the right subsets if state-of-the-art factoring implementations work in a manner similar to Zassenhaus. except that the combinatorial problem is translated to a lattice problem that is then solved by LLL. In this approach, LLL is not used to compute coefficients of factors. Instead, it is used to compute vectors with entries in 0, 1 that encode the subsets of that correspond to the irreducible through factors. Factoring over algebraic extensions, we can factor a polynomial, whereas a finite field extension of. First, using square-free factorization, we may suppose that the polynomial is square-free. Next, we write explicitly as an algebra over. We next pick a random element. By the primitive element theorem, generates over with high probability. If this is the case, we can compute the minimal polynomial of over. Factoring over, we determine that where corresponds to the element. Note that this is the unique decomposition of as a product fields. Hence this decomposition is the same as where is the factorization of over. By writing and generators of as a polynomials in, we can determine the embeddings of an into the components. By finding the minimal polynomial of in this ring, we have computed, and thus factored over bibliography. An example of degree 2401, taking 7.35 seconds, is found in section 4 in Hart, van Hoeij, Novacene. Practical Polynomial Factoring in Polynomial Time ISIC 2011 Proceedings 163 to 170. M. van Hoeij. Factoring Polynomials and the Knapsack Problem. J. of Number Theory 95 167 to 189. Froelich, A., Shepperson, C. On the Factorization of Polynomials in a Finite Number of Steps. Mathematische Zeitschrift 62, DOI 10.1007, BF 0118064, ISSN 00255874. Traja, B.M., Algebraic Factoring and Rational Function Integration, Proc. SYMSAC 76 http://dl.acm.org/citation.cfm =8063338 External link in Journal Bernard Busamy, Per and Flo, Paul Wang. Quantitative estimates for polynomials in one or several variables. From analysis and number theory to symbolic and massively parallel computation. Mathematics Magazine 67, 243-257, DOI 10.2307, 2,690,843, JSTOR 2,690,843, Cohen, Henry, A Course in Computational Algebraic Number Theory, Graduate Texts in Mathematics 138. Berlin, New York. Springer Verlag. ISBN 978-3-540-55640-4. Mr. 1,228,206. Kaltofen, Eric. Factorization of Polynomials, in B. Buchberger, R. Luz, G. Collins, Computer Algebra. Springer Verlag. Citesiac. 10.1.1.39, 7916. Nuth, Donald E. 4.6.2 Factorization of Polynomials. Semi-numerical Algorithms. The Art of Computer Programming 2. Reading, Massachusetts. Addison Wesley. pp. 439 to 461, 678 to 691. ISBN 0-201-89684-2. Lenstra, K. Lenstra, W. Lovis, Laszlo. Factoring Polynomials with Rational Coefficients. Mathematische Annalen 261, 515 to 534. DOI 10.1007, BF 014574454. ISSN 00255831. Mr. 682664, van der Waerden, Algebra, Trans. Blum and Schulenberger, Frederick Ungar.